This video will aim to explain what I refer to as part neutralisation calculations. So this is where we've normally got some strong acid, some strong alkali, we add samples of them together and we need to work out the resultant pH. So what we need to do to start with is to look at how many hydrogen ions we've got and how many hydroxide ions we've got, and we need to do this in terms of moles, which probably means that we're going to do concentration times volume, and what we need to decide is which of them is in excess. So whichever you've got a larger number of, so if you've got more hydrogen ions, you're going to end up with an acidic solution. If you've got more hydroxide ions, you'll end up with an alkaline solution. Once you've done that, you just need to remember that you've added two samples together. So what is the new total volume? And then you can work out the resultant concentration from the moles divided by the volume. First example of this is fairly straightforward. We've just got some hydrochloric acid and some sodium hydroxide. So the moles of hydrochloric acid, which is also going to be the moles of hydrogen ions, is just the concentration times by the volume, which we can see is 2.5 times 10 to the minus 3. In the same way, the moles of hydroxide ions, our concentration is half of that, and the volume is less, and that's 5 times 10 to the minus 4. So who's in excess? Well, hopefully we can see that we've got more hydrogen ions than we have hydroxide ions. So the moles of hydrogen ions left over after the reaction, we do the moles of the hydrogen ions, subtract the moles of the hydroxide ions, and that gives us just 2 times 10 to the minus 3. The new volume, well, we had 25 with the acid and 10 with the alkali, so our new volume is 35 centimeters cubed. So we've got the moles of the acid and we've got the volume, which means we can work out the new concentration of the hydrogen ions. And that comes out to be approximately 0.0571 moles per decimeter cubed. So we're nearly there. So the pH of the solution is minus log of the hydrogen ions and I'm getting 1.24 to 2 decimal places. Very similar example. This time we've got sulfuric acid, and at the top there I've just reminded us that when sulfuric acid dissociates in solution, just need to be careful, we get 2 hydrogen ions from each mole of sulfuric acid. So when we're working out the moles of hydrogen ions, we need to do the concentration times the volume, but now times by 2. And we should get 3.6 times 10 to the minus 3. Now for the hydroxide ions. And that's 4 times 10 to the minus 3. So in this case, it's the hydroxide ions which are ever so slightly in excess. So to get the moles of hydroxide ions in excess, we'll take one from the other, and that gives us 4 times 10 to the minus 4 moles of hydroxide ions. The new volume, we've got 40 and a 60, which makes it nice and easy. So the new volume is 100 centimetres cubed. So the new concentration of hydroxide ions is going to be 4 times 10 to the minus 4 divided by 0.1, which is going to be 4 times 10 to the minus 3. At this point we're going to need to use kW to access the hydrogen ion concentration. Again, we'll assume it's 298 Kelvin, so kW is 1 times 10 to the minus 14, and we're going to divide that by the new hydroxide ion concentration, which was 4 times 10 to the minus 3. And hopefully we're getting 2.5 times 10 to the minus 11, so nearly there. pH is minus log of the hydrogen ion concentration, which of course is very small, and we should be getting 10.60. Well done if you spotted a deliberate mistake there. So I didn't change in the calculator my concentration, which means those last two numbers were out. So we should have got 2.5 times 10 to the minus 12, and then our pH should have been 11.60. Sorry.